So last week we ended with conic sections and what a conic section was, and parabolas, looking at parabolas left and right facing as well as up and down like we had done previously in the course. Conic section, basically we looked at how it got its name by looking at these cone shapes and the different slices that you could take, and different things slices you could take and the different shapes you would get back. So today we're going to look at ellipses and hyperbolas, the last two. We looked at circles previously in this course, and we just did parabolas left and right, where we had also done up and down before. So the definition of an ellipse. So an ellipse is a collection of points in a plane where the sum of the distance from two fixed points called the foci. So the fixed points are called the foci. It's a constant distance, or is a constant. Okay, so it's a little confusing, the definition, but basically if you think of it with this picture, it makes it a little more intuitively sense. So let's think of 2 points. So there's 2 fixed points. These are called our foci, which is plural for focus. And we talked about the focus of a parabola before. So you have these 2 fixed points in here. And if we look at summing the distance, so let's say the distance between here and the distance between here, it's going to be the same anywhere along this ellipse. So if you think of taking a point or a string, let's say you have a string, and I'm going to show you. I have something that could represent a string, but basically if you have a string and you put them on 2 points and then you made it taut and keep it on those 2 points, if you move it around, it would make this shape of an ellipse every point that it took. So if you sum this distance plus this distance, anywhere you put it, it's going to be the same. So kind of think of it as this is a string in here. Here maybe is a tack where your strings are. And if you move your pencil's keeping the string taut. If you moved your pencil, we would get something that maybe looked like this. And so anywhere that you did this, so if I chose a different point and I looked at the sum of the string from here to here, that would be the same as it had been from here to here. So any point on this plane that is an equal distance is the ellipse. Okay, so don't worry about this too much, this definition. We need to focus more on we need to focus more on how to get the equation or how to graph it in the form that we can do this. So I'm going to start out with a lot of different kind of definitions and terminology that's going to help us. So an ellipse can face 2 separate ways. It can be elongated this way, or it can be elongated this way. So just like a parabola we talked about could be up, down, left, or right. In this class, we're going to look at ellipses that are either elongated, I call it with the x-axis, or elongated with the y-axis. You have 2 points that are always inside the ellipse, and these 2 points are called the focus. If we draw a horizontal and vertical line, so if I draw a horizontal line through the focus, this horizontal line is called the major axis. Major axis. The major axis is always going to have the same length for ellipses, and the major axis, the length is always 2a. So 2 times a. And we'll talk about how to find a in a minute. Just like a circle, your ellipse has a center. And so that major axis also goes through the center. And our center, just like a circle, we said was HK. So same thing here. Our center we're going to call HK. And then we have what is called the minor axis. The minor axis is the axis that goes through the center. So the minor axis. So it's always the smaller one of the ellipse, of the major and the minor axis always has the length to be. Okay, so those are going to help us. So it depends on which way your ellipse is elongated, depends on which formula you're going to use. Ellipses are always in the following form. So if it's elongated, where I call the major axis is parallel to the x-axis, our formula is going to be the following. So x minus h, in that parentheses, and then quantity squared. This is all over, so it's a fraction, a squared. And then we're going to have plus another fraction, y minus k quantity squared, all over b squared is equal to 1. Okay, so on this, we can see what the center is, hk. This value of a, I was talking about a here. Well, we said that the major axis was 2a. So basically, a 1a here and a 1a here. So these are kind of major points to help us graph our ellipses. So vertices of the ellipse on the major axis Okay, well, if we know where our center is at HK, then if we add our value of A to the right, we would get a vertice, and that's affecting our X value. So think of it this way as H plus or minus A. Oops. And our Y value, when we're moving left or right, is staying the same. So our Y value is at K. this vertice of our minor axis. Well, we talked about the minor axis, that total length was 2b. Well, the length from the top to our center is b, and from our center down, that length is b. So vertices on the minor axis, that's affecting our y value. So our x value is the same for our center, but we're affecting our y value. We're either adding our b value or subtracting our b value from that y value to get the vertices on the minor axis. Okay, so then there's one other point, which is the focus. So sometimes you want to find the focus, or sometimes you're given the focus and you want to find the equation, and this can help us. The focus, those are always on the major axis, and the value of here is C. So if I go from my center and I go, in this case, left or right C, I'm going to be affecting my H value of my center. So H plus or minus C, my Y value stays the same. So looking at our ellipse when it's in this form, you can see that you can figure out what A is, and you can figure out what B is. We could look at the square root of these squares. To figure out what C is always going to be the same value, and you can get it as C squared is equal to A squared minus B squared, or C is equal to the square root of this. Okay, so we kind of did this when we were looking at the focus and the directrix. We were adding and subtracting from our center depending on if we were going left or right, up or down. So same sort of idea with this with the ellipse. And if our equation was not in this form, we can always put it in this form. Notice that you have a perfect square here and you have a perfect square here. This is always going to be set equal to 1. So a little bit different than our circle. Our circle was always equal to r squared. Okay, so this was if major axis was parallel to the x-axis. Now let's look at it the other way. So if our major axis is parallel to the y-axis, okay, in that form, our equation for an ellipse in standard form is the following. So x minus h, quantity squared, all over b squared, plus y minus k, quantity squared, all over a squared is equal to 1. So major axis parallel to the y-axis. So notice that's almost identical to the equation we just set up here, where the major axis was parallel to the minor. I'm sorry, it was parallel to the x-axis. I was reading. The difference. So major axis we always said was 2a. So this length in here is 2a. The minor axis was smaller. This value of b is going to always be smaller than a. If it was equal to, it would be a circle. And if this value was bigger, then it's now going to be elongated the other way. And so a is always bigger than b. for an ellipse. So it depends on, looking at our denominator, which value is bigger. If the bigger value is underneath the x terms, then it's going to be parallel with the x-axis, is how I remember. And if the bigger value is underneath the y values, then it's going to be parallel with the y-axis. So look to see if the bigger number, if the number is bigger under the y terms or x terms in standard form. Okay, so kind of the same process. We can then, knowing this information, we can figure out what the major and minor vertices are going to be on the ellipse when it's elongated with the y-axis towards. And this was wrong when I said this was 2a. The whole length is 2a, but that one piece was each a. So if I want to look at this, our center is still at HK, but vertices on the major axis well, this time we're either going up or down a value of a from our center. And so up or down, that's affecting our y value of our point. And so our x value stays the same, h, but our y value now is either adding a value of a or subtracting a value of a to get to those 2 points. On the minor axis, we have this time our x value is changing by b, either adding or subtracting b to get to those points, so h plus b or h minus b, but our y value of our center is staying the same, which is k. And again, c is the same thing as the square root of the bigger number underneath the denominator minus the smaller number. And our focus, to get to our focus, that's on our foci. That is on our major axis, which is parallel to the y-axis. It's going to affect our y value to get from the center to our focus. And so our y value, that tells me my x value of my center is the same, and my y value is going to be plus or k plus or minus c. Okay, so looking at an equation in general form when it's not in this form where you can tell what the center is and information about the ellipse, you should be able to still look at it and kind of identify what the shape is going to be, if it's going to, what conic section it's going to be. If it's a circle, your values in front of x squared and y squared are going to be the same. And if it's a ellipse, the coefficients in front of our x squared and y squared are not going to be the same, but they're going to be the same sign. With circle, we were able to divide everything through by our coefficient in front of x squared and y squared and make it 1 so we could complete the square. Well, if our coefficients are not the same in front of x squared and y squared, we can't do that to complete the square. And so we have to manipulate it a little differently when we complete the square this time. And so let's look at the following. And so let's say, well, let's first start with this. So let's say you have x minus 3, quantity squared, all over 4, plus y plus 1, quantity squared, all over 9, is equal to 1. So analyze each equation, that is, find the center, foci, vertices of each ellipse, and then graph each equation. Okay, so looking at this, you should be able to determine the center. Once I determine the center, I also want to determine which way does my ellipse face. Is it elongated with the x-axis or the y-axis? So again, to determine that, look for the largest value, and 9 is bigger than 4. 9 is underneath my y terms. So that tells me that it's elongated with the y-axis. So my center again is at HK. And my H value, opposite sign, when this is a quantity squared, and it's in this form, opposite sign, so it's going to be positive 3. K, opposite sign, so negative 1. So I know A squared is the biggest number underneath here, so A squared is 9. That means that A is equal to 3. So, and I also know what this point is. That point was the center, which was at 3, negative 1. Okay. So I'm affecting my y value, my y coordinate from the center. And so my y coordinate, I have 3, and then I'm going to go up and down A, and my y, my x value is going to stay the same. So, sorry, 3, and then my y value is negative 1, and I'm going to go plus or minus my A value, which is 3. So I have 3, and then negative 1 plus 3 is 2. And 3, and if I do negative 1 minus 3, I get negative 4. My b squared value, that's the smaller value underneath in the denominator. So b squared here is equal to 4. So b, because we're talking about distance up and down, is 2. And so going left and right, 2 from my center, well, that's 3 plus or minus 2. And my k value is staying the same, which is negative 1. So my minor vertices, well, 3 plus 2, that's 5, negative 1. And 3 minus 2, this is 1, negative 1. Really, I don't need the focus when I'm graphing it on my x and y axis. But we have a center at 3, negative 1. And then we have major vertices at 3, 2, and 3, negative 4. those. So we have one at 5, -1, 1, -1. These are the minor vertices. And then what did I say? 3, 2, and 3, -4. So now graph the ellipse shape. So we should be able to, from here, we should be able to figure out what our x-intercepts are. Looking at this, I can tell that it's not crossing the y-axis. If I didn't know that and I went to go solve for my y-intercept, I would be getting a complex number back, an imaginary number, as a solution. And that should tell me that it doesn't cross. Okay, so this one was already in standard form, that I could tell what the center was and my A and B value. So sometimes it's not given in that form, and so we have to complete the square. So if we had 4x squared plus 3y squared plus 8x minus 6y equals 5. Okay, so same directions. We want to graph this. We want to find the center. We want to find the major and minor vertices and the foci. And I forgot to do the foci up there, but I'll just do it in here. So if it's not in that form where we can tell all that information, the process that you want to do is similar to what we had been doing with the circle. We want to group our x terms together, and we want to group our y terms together and get the constant to the other side. So let's just rewrite this a little bit. And so regrouping it, I have 4x squared plus 8x. I'm not going to leave room right now for a constant because I have a problem completing the square because my coefficient in front of the x squared is not 1. So let's just group the terms together, and later we'll leave some more room. And so this is plus 3y squared minus 6y is equal to 5. Okay, so in order to complete the square, our coefficient in front of the square had to be 1. We want to complete the square on the x terms and the y terms. Again, we can't just divide through by 4 because then I get 3/4 here, and that wouldn't be 1, and I couldn't complete the square on the y terms. And then when I tried to undo that or divided everything through by 3, I wouldn't get a 1 here. So I have problems when it's an ellipse. Circle, no problem, we could just divide through by it. So to counteract that, what we're going to do is we're going to factor out that leading coefficient in front of each square. So for my x terms, I'm going to factor out the 4. And for my y term, I'm going to factor out the 3. And once we do that, then we can complete the square inside those parentheses, because that coefficient we just manipulated to be 1. And so here, if we pull out a 4, we'd be left with x squared plus 2x. So common error, students want to factor out the variable x2 that they share in common, and we don't want to do that, so don't do that. So to make this coefficient 1 in front of the y squared, we're going to pull out a positive 3. And if we do that inside the parentheses, we're left with y squared minus 2y. We're going to leave some room here because we're going to add something to make this a perfect square. This is equal to 5. The thing is, if we're going to add something on the other side of the equal sign, then we need to add something on this side of the equal sign to make it remain equivalent. And so we're going to have to add something here. And we're going to have to, for the x terms and for the y terms. This, though, we need to be a little bit careful, and I'll explain why in a minute. So inside the parentheses, so remember we were looking at half of what the b value was once a was 1. So what was the same number you could add to give us this b value? So half it, 2 divided by 2 is 1. 1 plus 1 is 2. And then multiply that value, the half of that, by itself to get you what the c value was. So 1 times 1 is 1. So we're going to add 1 inside the parentheses to make this a perfect square. Same sort of idea for our y terms. Half the -2, we get -1. -1 times -1, that gives us a +1. So adding 1 inside the parentheses would make this a perfect square. The problem is we didn't technically just add 1 on this side inside. Because we put it inside this parentheses, we actually technically added a 4 on the side of the problem, because this 4 has to be distributed to each term. So we technically added this 4 in here. So we added 4 on this side. So we have to add 4 on this side. And so same sort of idea. Inside, we'd technically be distributing this 3 to drop this parentheses. So we really didn't add 1 on this side of the equal sign. We added 3 times 1. So we added 3. So if we add 3 to this side, then we have to add 3 to the other side. Okay, so we can now rewrite these as perfect squares. This is 4 all times the quantity. So the same thing that multiplies to give us 1 and adds to give us 2. Well, we made it so it was a perfect square. That's 1. So this is x plus 1 quantity squared plus 3. And then the perfect square for y squared minus 2y plus 1, that's y minus 1 quantity squared, is equal to 5 plus 4, 9 plus 3, which is 12. So once you complete the square, you're not quite done. Your form for ellipse was always set equal to 1. And so you divide both sides by that number, that constant on the right-hand side or the other side of the equal sign. And usually that coefficient up here simplifies and cancels. If it doesn't, then we have to manipulate it and rewrite it, because the coefficient in front of our quantity squared in the numerator was always 1. Okay, but this case, we need to set this equal to 1. For ellipse. See that that's also true for hyperbola. This is always going to be equal to 1. So for ellipse, this needs to be 1. And we don't do this step until we have the perfect squares. So I will not have started up here at this top and divided everything through by 5. That would have just made my life really complicated when I had to pull out a coefficient. Okay, so it needs to be 1. So divide this by 12. Technically, I'm dividing each grouping on each side of the equation by 12. And so 4 all times the quantity x plus 1 quantity squared over 12, things simplify. And 4 goes into 12 3 times. And so we're left with x plus 1 quantity squared over 3 plus, so again, things simplify. 3 goes into 12 this time 4 times. So we have y minus 1 quantity squared all over 4 is equal to 1. So it's now in the form. It actually almost looks identical, but not to what we had before. So I can tell which way it's elongated. Look at the larger number underneath in our denominator. 4 is bigger than 3. So the larger number tells me that it's elongated with the y-axis, major axis is. I can tell what our center is, HK. So that would be -1, opposite sign, comma, opposite sign, +1. My a squared value is 4. So take the square root of that. A is 2. This is b squared. So b squared is 3. So b is √3. So once I knew that, I really wouldn't even go through and find my points of my vertices. I would just plot. So I have a point I know at -1, 1. There's my center. My major vertex I know is 2. I made this big so I could make them more, but I'm going to change it. So I know I need to go up 2 from here because my major axis is parallel with the y-axis. So that would get me a point right here. So I could just tell right away that this is at -1 and then +3. If I went down 2, that now gets me at a point when x stays at -1, but my y value now is -1. B is a little more difficult in this case because it's a square root. Square root of 3 is, I believe, 1.7, but let me see. 1.73. So I would go left and right, 1.73, and this is why I was trying to make my intervals a little bigger, but then I was gonna run into the stuff above. So if I go over 1.7, so just approximate. And I can do this as, let's write it as -1. We were adding a √3, comma, and then my y value is the same, which was 1. So if I subtract 1.7, so this would have been -1 minus √7. Sorry, not √7, √3, comma, -1. And then just draw our ellipse. So I can tell that this is crossing both the x and the y axis. I can find my x-intercepts by setting y equals 0 and solving from my x. I can find my y-intercepts by letting x equals 0 and solving for y. My focus, I technically really didn't need those to graph, but I can find them. And my c value, because I have to either add or subtract c from my center, c is equal to, or c squared is equal to a squared minus b squared, the bigger one minus the smaller one, or c is equal to the square root of, well, a squared. These are already in the form of a squared and b squared. So 4 minus 3. So c is equal to square root of 1, which is 1. So technically, if they wanted those points, I'm going up and down from my center, 1 And my center was, what was it, -1. So I have one focus at -1 plus 1. That's 0, 1. And I have one at -1 minus 1. So that's at, oh, sorry, wrong one again. I'm doing my y value. So x is going to stay the same, -1, but I'm going to add or subtract from my y value. Okay, so I have one at -1 and 1 plus 1, which is 2. And I have one at -1, 1 minus 1, which is 0. My focus is really here. Foci, again, is just plural for focus. And there are multiple ones in an ellipse, 2 of them on the major axis. So that they're not too bad if you know how to complete the square and recognize the form. And ellipses are almost identical to what we just did. But let's look at, given information about an ellipse, finding the equation. And so similarly to parabolas, when we were given information about the parabola and we were trying to find the equation, it was helpful for us to plot and graph what we were given. And given that information, then we could tell which way last week the parabola was facing by where our directrix and our focus was. This time we can determine which way our ellipse is elongated towards the x or the y-axis by information we're given about the graph. Okay, so find the equation for the ellipse. So if you are given that you have a focus is at 0, -4, and vertices is at 0 plus or minus 8. Okay, so let's plot what they're given, and then let's determine which equation we're going to use for our ellipse. And so if we plot 0, -4, this is a focus. And then 0, +8, and -8. Okay, so knowing that, we can tell right away, or hopefully I can tell, hopefully you can also tell, that our major axis is parallel to the y-axis. It's actually on the y-axis. So we have the major axis is on the y-axis. So we know what form we're going to use. It's going to be x minus h, quantity squared, all over, plus y minus k, quantity squared, all over something equals 1. Well, if the major axis is parallel with a y-axis, then the a value, the bigger number, is going to be underneath the y. So a squared is going to go underneath the y. And so that means my b value, the smaller value, is here, b squared. So also plotting things, I can also tell right away certain things. In this one, notice our center. If I have a major vertex at +8 and I have a major vertex at -8, my center is always halfway in between. So this must be my center. Remember the major axis? That length was 2a. And so our a value was the distance 2 when we were looking at plotting these, was going up and down a from our center. So we can look at this and we can see that then a has to equal 8. For my equation though, I need a squared. A squared then is equal to 64. C is the distance between the center and the focus. And so if I look at this, we were given that the focus was at 0, or one of the focus was at 0, -4. And so we know that this distance here is my C value, and so C must equal 4. So we're almost there. We need to figure out what B is. We know what A and C are. We have the formula that says that C squared equals A squared minus B squared. So C squared equals A squared minus B squared. So C we said was 4. So we have 4 squared is equal to A squared, which is 64. Minus B squared, which we're trying to find. So 16 equals 64 minus B squared. If I subtract 64 on both sides to get B by itself, I can use my square root method. So what do I get? 64 minus 16. 48 is equal to B squared. I technically don't care what B is offhand. Actually, I would if they told me to graph it, which actually part of the problem did. But for now, for finding the equation, it wants B squared, not B. So we know what B squared is, we know what A squared is, we know what our HK is, and so we now know what the equation of this ellipse is. So H is 0, so we have X quantity squared all over B, which is B squared, which is 48, plus my Y K value is 0, so Y minus 0 quantity squared, so Y squared all over A squared, which was 64, equals 1. To graph it, we're almost there. We know what 2 of the vertices are. We know what B is. Well, we know what B squared is. B squared is 48. So B is the square root of 48. So let's look at the square root of that. Estimate it so we can graph it. We get approximately 6.9, which makes sense because 49, the square root of 49 is 7. So we'd have to go left, right from the center, 6.9, and then we could get the graph. So from that, we got the graph given the information and the equation. I'm gonna blow this up just because I want my pen to be thicker. So let's say you're given the center is -3, 1. You're given that you have a vertex at -3, 3, and you have a focus at -3, 0. Find the equation of the ellipse. Okay, so again, graphing sometimes is really helpful because that helps us get our equation. So center is -3, 1. 1, 2, 3, 1. So just put it here. So I have -3, 1. So I know what my H value is -3. I know what my K value is. It's 1. So my vertex, it only gives me 1. My vertex is at -3, 3. So if I go over 3, up 3. And then my focus is at -3, 0. Okay, so that tells me I can figure out some values, again, to help me. This one's similar to what we had done before. It's just that this one's shifted and not, the center's not at 0, 0. Our vertex is here. We have our center here. So we could figure out what A is. Our value A is 2, going from a 1 to a 3. Our focus gives us our C value. From the center to our focus is our C value. I guess that. And so that is just 1. So we know what A and we know what C is. C squared equals A squared minus B squared. So we got C squared is 1 equals 2 squared is 4 minus B squared. Subtract 4, we get -3 equals -B squared. Divide by -1, B squared equals 3. So B is √3. Although for our equation, we don't need to know that. So it's x minus h, x minus a -3, so that's x plus 3, quantity squared. Let's just go over here, plus y minus k, so y minus k is 1, y minus 1, quantity squared, all over something equals 1. So again, we need to determine if there's a bigger number underneath the x or the y. It's elongated. The focus is always on the major axis. So the major axis is parallel to the y-axis. So my A value has to go underneath the y values. And so 4 is underneath here, and b squared is underneath the x, which is 3. Okay, so there's this really cool thing called the whispering room. Basically, if you have an elliptical room, and so I believe there's a, let me just read it. It's a whispering gallery. A hall 100 feet in length is to be designed as a whispering gallery if the foci are located. Basically, if you have this elliptical room and you place 2 people on the foci of that ellipse, and it could be a huge room, and there could be lots of different people in this room, and these 2 people were standing on these foci, they could whisper, and the sound would bounce off, and the other person could hear them. So that's, and I believe the Science Museum actually in San Francisco, I think there's some place in there that you can do that. But it could have been a while back. So anyways, let's look at an example. So we're going to be given information, and then we're going to, well, let's answer the question. So it says, Jim standing at one focus of a whispering gallery is 6 feet from the nearest wall. His friend is standing at the other focus 100 feet away. What is the length of the whispering gallery? How high is its elliptical ceiling at the center? Okay, so basically, we got some different information. We got one person who's standing here on the foci. And he is 6 feet away from the nearest wall. Do we know that that's right there? His friend is standing on the other focus. And we're given that that's 100 feet away. What is the length of the whispering gallery? And what is the height of the elliptical ceiling? And the height of the ceiling at the center. Okay, so let's change my picture a little bit. Makes more sense. Okay, so we want to figure out what is this distance in here. I can actually probably figure this out without doing anything, right? This is 6 feet. We know this length is 100, so this would have to also be 6 feet. So if we added 6 feet plus 100 feet plus 6 feet, which is 112 feet, Now we need to figure this out. Okay, so we got some values that we know. We can say our A value. Our A value is the bigger value, and it's the length. Our length of the major axis is always 2A. So we know that 2A is equal to 112. So knowing that that length is always 2A, if we divide by 2, we get A is equal to 56. So that's going to be useful. And then we also know B or C, and that can help us find B. So that distance from the center to the foci. Well, if this whole distance is 100, half of that distance is 50. And so if we go here, 50, so we know that C is equal to 50 feet. We need C in order to find what B is, and B is that height. Well, we know that C squared equals A squared minus B squared, or another way to say that is B squared is equal to A squared minus C squared. Just manipulating and solving for B squared. So B squared is equal to A squared, which is 56, minus C squared, and C is 50. So we get B squared is equal to 536. Right. B squared is equal to 636. And so take the square root of that. We get that it's approximately, B is approximately 25. Go back to directions. I think it said round to the nearest tenths. So it's 25.21. So rounding to the tenths, I'd have just 0.2 B is the height of the building at the center. Of the room. Okay, so hyperbolas. Hyperbolas is almost identical to ellipse. There's only one minor change in what the equation looks like. Instead of a plus in between those fractions, there's a minus. So hyperbolas let me just read you. I'm not even gonna write it down, but let me read what the definition says. So a hyperbola is a collection of all points in a plane, the difference whose distance from the foci of fixed points called the focus is a constant. So instead of the sum of the distance from the fixed points, it's the difference from those distance of the fixed points. So there's two ways parabolas or hyperbolas could be facing. I think of these kind of like parabola shapes facing away from each other. So hyperbolas, they could either be facing those parabola shapes away from each other towards the y-axis, up and down, or it could be facing left and right. So just like with the ellipse, let's look at this with some terminology. And so this point that in between what are called like these vertices of those hyperbolas, this is what our center is. And that again is at HK. The center is actually not a point on our hyperbola, but it helps us get that shape. Our focus, just like our focus weren't points on our parabola or ellipse, our focus, our parabola shapes of the hyperbola are facing towards the foci. So depending, are we going to go up or down, left or right from that center to get that? And then we have these points here, kind of like the vertex of a parabola. And these are vertices of the hyperbola. I've been skipping each time, giving you the definition centered at 0, 0. I've been just jumping in and putting in the center of these conic shapes being at any point, HK. Okay, so terminology, they call this axis that joins these vertices the transverse axis. So really, we're thinking, is our transverse axis parallel to the x-axis or y-axis when we're determining which equation we're using? We also have what is the minor axis, but let's talk about that in a minute. So let's just take a break, and then come back and we'll look more at hyperbolas. Okay, so we were just getting into terminology of hyperbolas, and I had to check on what the axes were called and make sure they were called the same thing in this textbook. And so I was right. So the transverse axis, this is the axis that is going through your center, your vertices of your hyperbola, and your foci. the length here is A, and this length is A. And so the length between the two vertices is...
Professor?
Yeah.
I think your screen share is off.
Thank you so much. There we go. So hopefully you should see that now. This over here. Okay, so the transverse axes, that was with going through the X and the vertices. It's always parallel, either parallel with the y-axis in this case, or the x-axis in this case. This is always your A value between the center and the vertice on the hyperbola. A is not necessarily bigger than B like it was for an ellipse. Then we have what is called the conjugate axis. So the conjugate axis goes through the center. It doesn't, I guess it helps us grasp some stuff, but it's not part of the graph. We're going to try to find some value. We're going to find some value B, and it could be bigger up here. It could be smaller down in here. That actually helps identify how wide these parabola shapes of our hyperbola are going to be. And so we're going to go some length of B on here, depending what it tells us. So we're either going to go up or down from our center, or we're going to go left or right from the center. So points on the minor axis. Oops, I'm going to call it minor axis, conjugate axis. And points at the vertices. Help us make a rectangle and that rectangle helps us to then identify where your asymptotes are going to be for your hyperbola. There's two asymptotes that this is going to be following. So points of the conjugate axis and points on the vertices help us make a rectangle. Which helps us identify where the asymptotes occur. So just kind of bear with me, I'll help you with that in a minute. But let's go back to the direction our hyperbola is facing and the equations that will help us find the center, what our A value is and our B value is, and help us graph. So again, it depends on which way we're facing. So hyperbolas, if it's a facing towards, I think of it as facing towards the x-axis, then our transverse axis is parallel. To the x-axis. And if it's facing up and downwards, this transverse axis is parallel to the y-axis. Okay, so if it's parallel going left and right, and it's parallel to the x-axis, our form is going to be x minus h quantity squared all over a squared minus y minus k quantity squared all over b squared is equal to 1. Where our center is going to be at hk. Even though it's not really a point on our graph, it's going to help us with graphing it. And then our vertices, we're going to have 2 of them when they're facing this way. And this value is A. So again, if I look at, so I don't have these memorized, I just do it by looking at it and thinking about it. I'm going to add and subtract, and that's from my x value. So h plus or minus a, and my y value would stay the same. Okay. My focus, or foci, because it's plural. This is where your parabola is facing. So if it's facing left and right, we have points here. And we're going to either add or subtract c from the x value of our center. And so our foci would be h plus or minus c. Our y value is staying the same there, k. We want to go up and down. These aren't points I usually find, but we want to go up and down b from our center. To help form a rectangle. So let's say we had some b value here and some b value here. So what we're going to do is we're going to form a rectangle with these vertices and these b values. So basically we want to go like this. And so once we formed our rectangle, we want to make diagonal lines going through the center and the corners of our graph, or corners of our rectangle. So these hyperbolas actually have an oblique asymptote, or slant asymptote. So these hyperbola shapes are going to start growing towards these linear lines as we go off to positive and negative infinity. So we have asymptotes. I never had this memorized, but it didn't look too bad this time when I was looking at it again. It's y minus k. So think of it as a vertical shift, k, equals, well, we're doing a ratio of our a or b value. So plus or minus b over a all times x minus h. Technically, I wouldn't have this memorized. I know I could find 2 points easily. One of them is the center, easily on my graph, and I could find out what that equation of line is by given 2 points. Okay, one thing to know here is that A is not necessarily bigger than B. A, we determine what A is by which part is positive. Notice there's a minus in front of the y terms. So the x value is positive. This is how I know too that it's facing towards the x-axis, left and right. Your book gives you how to find b squared. I've always learned how to find c squared. C squared is always, instead of the difference, because we don't know a is bigger, we have a squared plus b squared. They give you the formula where they solve for b squared and say, well, b squared is equal to c squared minus a squared, which is helpful to know, but we don't need to know it that way, or you can memorize it that way. Okay, so if the hyperbola is going where it's facing towards, the parabola shapes are facing towards the y-axis, then our form is going to be as follows: y minus k quantity squared all over a squared minus x minus h quantity squared all over b squared is equal to 1. So center, again, is at HK. Be careful here because H is always with the X value, K is always with the Y value. We kind of talked about this when we were doing the parabolas. Here on our transverse axis, we're going to go up and down to get our vertices. And so you would add or subtract A to get that. And we're doing it from our Y value of our point. So our vertices is at H, comma, K plus or minus A. Foci is on the transverse axis. Our X value stays the same, so it's H, and then we're going to do the Y value of the center plus or minus our C value. We're going to go up and down B to help us form our rectangle, which then will help us form our asymptotes. And so asymptotes, it's y minus k is equal to plus or minus a over b, all times x minus h. And again, c squared is equal to a squared plus b squared, or b squared is c squared minus a squared. Okay, so let me grab some. Okay, so again, this equation almost looks identical to your ellipse. So we're going to be putting it in this form similar to how we were just doing it with the ellipse. Instead, this has a minus instead of a plus in between. I can tell by working with an equation when it's not in this form, if I'm dealing with an ellipse, I can notice if I have an x squared term, a y squared term in my equation, and I have opposite signs. So one is positive and one is negative coefficients in front of my either x squared term and y squared term. So if we had y plus 3 quantity squared all over 4 minus x minus 2 quantity squared all over 9 equals 1. So the direction says find the center, the transverse axis, vertices, foci, and asymptotes, and graph the equation. Okay, so looking at this, I can see what the center is. So HK, H is always a value with an X, so opposite sign. So it is +2. And my K value is with a Y, so it's -3. A is always with a squared is always with a +1. So A squared is 4. B squared is with a negative, so the 9. Which one is positive? Tells me which direction that hyperbola is facing. It's the Y terms that are positive right here. And so it's going to be facing up and down. So let's just plot what we have. So we have the center is at 2, -3. So if we go to right 2 and down 3, you have the center. So our vertice, because it's going up and down, we're going to go up and down A from this. Well, we need to figure out what A is. A is the square root of 4, so A is 2. So if I go up 2, here's the vertice of my hyperbola. And if I go down 2, here's the vertice of my hyperbola. So by just looking at that, I know what my point is. My Y value, my X value is at 2. My Y value is -1. And my X value is at 2. And my Y value now is -5. So I know it's going up, and I know it's going down from here. I just don't know how wide that is. Excuse me. Okay, so what can help me how wide that's going to be is by looking at my B. My B value in this case is 9. I'm sorry, my B squared is 9, so my B is 3. So I'm going to go left and right 3 from the center. Okay, so we want to form a box with this. So going through our vertices, and that point, we can form a box. And with that box, this is forming our line, our asymptotes. Sorry, it's not very good. So our graph, the Y value is positive. Oops. Yeah, it is. And so it's going up and down. And so it's going to get pretty wide because it's going to follow eventually these lines. So our graph, it's symmetrical across this horizontal and vertical line. So this vertical line going through the center and our vertices, our transverse axis, and our conjugate axis. So being able to plot our center, our vertices, and our B value, we can form our triangle, form our asymptotes, and be able to get a good shape of what the graph is. We could also find and identify more important points, our intercepts. Okay, so if it's not in this form, and we want to put it in this form, almost identical like we did with the ellipse. So let's say you're given x squared minus 2y squared plus 8x minus 6y plus 4 equals 0. So without this even being in, not in that form where I can find what the center is, I can tell right now that we're dealing with a hyperbola. Because if I look in front of the coefficient in front of the x squared, I have a positive 1. If I look at in front of the coefficient of my y squared, I have a negative 2. They're not the same number. If they were the same exact number, it would have been a circle. If they were the same sign, this would have been an ellipse. But they're opposite signs. One's positive, one's negative, so I know I'm dealing with a hyperbola. So similar to what we did with the ellipse, we want to complete the square on our x terms, our y terms. And so let's do that. We want to group our x terms together, our y terms together, and get the constant on the other side. And so we have x squared plus an 8x, and then minus 2y squared minus 6y equals, so subtract 4 on both sides to get the constant over there, minus 4 or negative 4. So before we can complete the square, the coefficient in front of that square term has to be a positive 1. So we're lucky, it's already done for the x terms. So we have x squared plus 8x plus, so we're trying to think to ourselves, oops, sorry, to the plus. We're trying to think to ourselves what we're adding in order to make that a perfect square. Well, half this, it's 4. So the same number that adds to give us 4, we need to multiply to get the c value. So 4 times 4 is 16. That should be an 8x. But if we add 16 on the left-hand side, we have to add 16 on the right-hand side. So unfortunately, we can't just complete the square on those y terms. We have to make that coefficient in front of the y squared a 1. And so we can factor out negative 2 from our y terms. And if we do that, we get a y squared plus 3y. We're going to add something in here to make it a perfect square, which means we're going to actually subtract something here, but let's add something here. A little different though. So we're going to half our b value, so 3 divided by 2. If I add 1.5 plus 1.5, I get 3. And so 3 halves times 3 halves is going to give me this value. Well, 3 halves times 3 halves is 9/4. So I need to add 9/4 in here to make that a perfect square. Okay, so I need to be careful because this is really negative 2 times 9/4. That's really what I added on this side of the equation. I can reduce this a little bit. 2 goes into 4 twice. So I really added negative 9/2 on this side of the equation. So I really need to do the same thing over here to make it equivalent. Add negative 9/2. Okay, so let's rewrite these as perfect squares. So x squared plus 8x plus 16, we manipulated to be a perfect squared, and that is x plus 4 quantity squared. Then we have this -2 outside, and then we just manipulated this y squared plus 3y plus 9/4 to be a perfect square, and that's y plus 3/2 quantity squared equals, well, -4 plus 16, that's 12. I'm going to need a common denominator. And then I have this minus 9/2. So my LCD is 2. I need a common denominator of 2 here. Okay, so x plus 4 quantity squared minus 2 all times 1 plus 3/2 quantity squared is equal to, so this is 24/2 minus 9/2 is 24 minus 9 is 15. (15/2). Not quite in standard form. We have to set this equal to 1. I could divide everything through by 15/2, then I'm dealing with complex fraction, or I can multiply by the reciprocal, and then I don't have to deal with that and simplify. So let's multiply both sides of the equation by 2/15. That would give us 1 on the one side that we wanted. Okay, I'm going to need to distribute that 2/15. And so this gives me 2/15 all times x plus 4 quantity squared minus, so 2/15 times 2/15 is 4/15 all times y plus 3/2 quantity squared equals 1. Okay, so again, we got a little bit of a problem because these coefficients, when we divided both sides by, or multiply both sides by 2/15 to make that 1, it didn't cancel things out, and it didn't make it a coefficient of 1 in the numerator. We need that coefficient of 1 to be in the numerator. So mathematics, again, is always just kind of rewriting things that are equivalent forms that will help us get it in the form that we want, and so that we can see. And so instead of having this as 2/15, think of it as division. If we divide by this reciprocal, then when we rewrite it, it's multiplying by the reciprocal. So we could technically, and this is the trick in this case, is rewrite this as x plus 4 quantity squared all divided by, so 15/2, the reciprocal of the fraction here. So this is identical, again, as x plus 4 quantity squared divided by 15/2. Division of fractions, you take the first times the reciprocal, which would give me back the equivalent of this. So do the same idea for the next piece. So we got minus, and then we have y plus 3/2 quantity squared, all divided by the reciprocal of 14/5. Reciprocal of 14/5 is 15/4. is equal to 1. Okay, so we got it in the form that we now wanted. We can tell what the center is. We can tell which direction it's facing. So the center, opposite signs, h is always with the x, so we have a -4, comma, -3/2. Depending on which one is positive. So it's facing towards the x-axis, so it's like this. Your a squared is always with the positive, so a squared equals 15/2. B squared is always with a negative, so that would be b squared is 15/4. Okay. I just kind of wanted us to analyze the equation. We could go further and graph it if we wanted to. For time's sake, let's not. Let's look at one now where you're going backwards, where you're given information, and now we're trying to find the equation. We'll get some more practice, and hopefully in a minute, with graphing more of these when we look at the nonlinear systems. So find the equation for the hyperbola described. So your center is at 1, 4. Your focus is at -2, 4, our focus. And you have a vertex at 0, 4. So find the equation of the hyperbola. Okay, so again, you want to plot these points and what they give us so we can kind of determine which equation that we want to use. Plotting the point 1, 4. So going over 1, up 4. Here's my center. Focus is at -2, 4. And a vertex is at 0, 4. I know my vertex is always facing towards my focus. I also know my focus and my vertex and my center are all on the transverse axis. So I noticed that my hyperbola, the shapes are going to be facing towards the x-axis, positive and negatives. And so I also know then my equation is the x part is positive, so it's x minus h quantity squared. A is always with a positive, so a squared, minus y minus k quantity squared all over b squared equals 1. We know what h is, we know what k is. That distance between the vertex and the center, that length is a. So that length in here between x equals x equals 1 to x equals 0 is 1. So we know a is 1. That distance between the focus and the center, this is the length of c. Well, if we're going from x equals 1 to x equals -2, 1 minus -2, that gives me 3. And then I can figure out what b squared is. And this is probably why they say b squared equals c squared minus a squared. So we don't have to go in there and rewrite it. But basically, if we know c squared equals a squared minus b squared, actually plus b squared. So b squared is equal to a squared. A is 1 minus, oops, something's wrong. Sorry, c squared minus a squared. Getting a negative number, I knew that wasn't going to work. Raise. B squared is equal to c squared minus a squared. C squared, c is 3, 3 squared is 9, minus a squared, 1 squared is 1. So b squared equals 8. So if we go back in and we plug in our values, we got it. So we have x minus h. H is 1, so x minus 1. Quantity squared all over a squared. A is 1, so 1 squared is 1. Minus y minus k. Well, your k value is 4, so y minus 4, quantity squared all over b squared. B squared is 8, so all over 8 equals 1. You could rewrite that without the 1 in the denominator there, but you don't have to. So again, you should just be able to look at the equation. So it might just say, you know, identify the conic equation. So identify the graph of the equation without applying any, it says rotation of axis, but we're not doing that. That's wrong. Wrong section. So if we had, for instance, y squared plus 4x plus 3y minus 8 equals 0. Identify each of the conic without completing the square and without applying rotation of axes. Again, this book is going over some of the stuff that we're not going to cover, which that is one of them. So just by looking at this, you should be able to tell which conic section it is and which direction. So I'm looking at the equation. I first jump to where are my x squared and y squared terms? What's in front of those? And if there's not both the x squared or y squared term, then I know that that means it's a parabola. So there's not an x squared and a y squared term, so that's a parabola. And then I look at which one is squared. Normally we looked at before always graphing y equals x, something in the form of ax squared plus bx plus c, where the x part was squared and it was up and down. Well, this one, the y part is squared, so I know this is a parabola and it's either going left or right. So you should be able to go further and be able to put it in that form that we had before and then graph it and find important points. Same idea though, but if you were looking at the following equation, 9x squared plus 4y squared minus 18x plus 8y equals 23. So identify the shape. So again, go right into the equation and look for x squared and y squared. They both have an x squared and y squared, so I know it's not a parabola. Now look to see if they're the same number. They're not. And then see if they're the same sign or opposite sign. Same sign, ellipse, opposite signs, hyperbola. So same sign, this tells me this has to be an ellipse. I'd have to go a little bit further and put it into that form where I can see which way it's elongated by looking at which number was bigger under the x or the y. For ellipse, a squared is always bigger than b squared, but not necessarily so for hyperbolas. If we had 4x squared plus 10x plus 4y squared minus 9 equals 0. So looking at this, I notice I have an x squared and a y squared, so parabola's out. Number in front of x squared and y squared are both 4, same sign, same number, exact same number, we have a circle. Okay. So I'm going to tie this in together, and this is where I'm going to jump to a different section. So we're pretty much done with chapter 11. That's all we're covering in this book. I want to jump to nonlinear systems because graphing the nonlinear equations can be helpful for solving those systems. And there's no kind of right way or wrong way to do these. You just have to look at them and kind of see what looks best. Where there's kind of a certain format to go through when you're doing systems of linear equations, which we'll look at next. Let's do this. New page. So what I'm jumping into is 12.6 in our textbook, which is systems of nonlinear equations. Okay, so systems of equations, that's where you have multiple equations and your solution has to satisfy all of the equations in that system. There's multiple ways to solve systems of equation, addition or elimination method. They're the same thing where you're summing an equation together or summing a multiple of an equation and another one together so that variables go away. And then you can find the other variable, or substitution method. So in the following, it tells us to graph each equation of the system, then solve the system to find points of intersection. So for instance, if we have a system where we have y is equal to x squared plus 1 is one of our equations, and the other equation is y is equal to 4x plus 1. So a lot of this course has been on graphing and tools to help us graph. And so you should right away identify and know what that graph of y equals x squared plus 1 is. So the general shape would be y equals x squared. That plus 1, you should know right away that that's just shifting your graph of y equals x squared up 1 unit. And so if we look at that graph, you have a vertex then at 0, 1. You know, you normally had a point at 1, 1, but now it's going to be at 1, 2. Negative 1, 1. It's now at negative 1, 2. Okay, so I got a graph of that. Not the best, but I got a graph. And then I should be able to graph the other one, y equals 4x plus 1. Right away, I notice that that's a line, and it's already in slope-intercept form. So this is already in the form y equals mx plus b. So I can tell my slope is 4. Tell me graph 4 over 1. And I can tell my y-intercept is at 1. So by plotting that, I know I have a y-intercept at 0, 1. And then I know for every, if I rise at 4, I'm going to run over 1 to the right because it's positive. Or if I fall 4, I go 1 to the left. And so I'm going to have an equation that looks like this. My graph's not great. Okay. So from here, I can already tell that this is going to at least intersect in one spot, right? By just graphing it. I can tell that that is at the point when x is 0, y was 1. So we have at least one. An intersection. It's possible this is going to come back up like this. This is growing at a constant rate, so it's possible that they might intersect again. And I wouldn't know that unless I keep continuing to graph and see, or if I go now and look at this solving. Okay. So I can either, when I'm solving this algebraically, I can either use the substitution method or I can use the elimination method. If I use the elimination method, notice I can eliminate my y values by multiplying a -1 by one of them and summing them. My x terms wouldn't eliminate because one is squared and one is not. Or I can use substitution. They're both in the form y equals. We can just set these equations equal to each other. So either way, we're going to get the same result. And so using substitution to solve. So again, we have y equals x squared plus 1, and we had the equation y equals 4x plus 1. So we're setting our y's equal to each other. So we're looking at when is x squared plus 1. Substituting this in wherever I see a y here is equal to 4x plus 1. So using substitution, then you need to decide how you're going to solve for the remaining variable. So how we're going to solve for that remaining variable depends really on what type of equation we have. I notice this is quadratic, so I would want to get everything to one side of my equal sign and see hopefully that I could factor. So solve for the remaining variable. Okay, so I'm going to subtract 4x on both sides. So I'm still left with this x squared, a minus 4x. And then I'm going to subtract 1 on both sides. Well, my constants then cancel and then equals 0. So this factors, I can pull out an x. Factoring out an x, I get x times x minus 4 equals 0. There's two values which set this equal to 0 when x is 0 and when x minus 4 equals 0, or x equals 4. So we need to find the y value of the point. So this is the x value of the point. You need to find the y value. So you have to go back in here and you need to plug it into either one of these equations. This is where they're intersecting, so this is where your y values are going to be exactly the same. Okay. So we want to find the y values. Your points. So I can plug in 0 for x here or here. Notice I get y equals 0 squared plus 1 is 1. I plugged it in here, I get y equals 4 times 0 plus 1. So 4 times 0 is 0 plus 1 is 1. Same idea. Now plug in 4 wherever you see an x. 4 squared is 16. 16 plus 1 is 17. Y is 17. You want to check again. 4 times 4, plugging in 4 for x is 16 plus this 1 is 17. Okay, so we have 2 points where this graph is going to intersect. And so yes, when we go out a little further, so this is 1, 2, 3, 4. Up here somewhere, this would be a y value of 17.
How did you get 17?
When x is 4, go back and plug it in for y, or for x. So 4 squared is 16 plus the 1 out here is 17. Or if you plug it in here for this equation for y, if you plug in 4 for x, because that was our x value for one of the them, 4 times 4 is 16 plus 1 is 17.
Okay, thank you.
Yep. So noticing the solutions, it's possible. We've been dealing with, when solving equations, sometimes getting extraneous solutions. And so this is possible in these. And so you always need to go back actually and check to see if these works. If it's graphical like this and pretty easy to graph, it's easy to see what type of solutions or how many solutions that we're going to get and about where they are. So I knew that, you know, this would be in the first quadrant here. So if I got some negative number down here where it was intersecting, I knew that would be false because my parabola was facing upwards. And then I'm sure if I plugged it back in, I would get a false statement. Let me pull another one. So this system, you get y is equal to the square root of 4 minus x squared. And we have y is equal to 2x plus 4. Okay, so I want to graph this. This one's a little more difficult to see what it is. Notice if you square both sides of your equation, that would be in a y squared here. And I'd have a y squared equals 4 minus x squared. And then if I added x squared to both sides, I get something in the form of x squared plus y squared equals 4, which is what I do know what that looks like. That's a circle. And so the square root is actually just giving me a semicircle, half of the circle. And it's the top half of the circle because the coefficient in front of here is positive. So by squaring both sides of the equation, you can see this is a semicircle. centered at the origin. With radius 2. Because we get y squared equals 4 minus x squared, add x squared to both sides, x squared plus y squared equals 4. So let's just graph it. So from the center, we go up 2, to the right 2, and to the left 2. And that's that piece. The other equation is a line. Again, we have what the slope is, and we know what the y-intercept is. And so here I can tell my slope is 2, or 2 over 1, and my y-intercept is at 4. So plot a point at 0, 4. And if we rise 2 and go over 1 from the slope. I'm sorry, didn't do it right. Rise 2 over 1. Where if we go down 2 and over 1, down 2 over 1, doesn't look best, but okay, so right there, just because we plotted the same point, I can see that I'm going to get a point, my solution, at -2, 0. Because this is a semicircle, there's no other place that this can intersect unless they're somewhere right in between here or hitting in here and here. It's hard to see with my graph. So you got to determine which way you want to solve this. We can use substitution, where we substitute one value of y in for the other. It's already in the form y equals, so we can do that. And so if we use substitution, we have the square root of 4 minus x squared is equal to 2x plus 4. So I notice what type of equation I have. I have an equation with a radical. I can use the method where I can square both sides. It's already the form where my radical is already isolated. If it wasn't so, I would need to isolate it before I squared both sides. Some of you guys were forgetting to do that. So squaring the square root leaves me with the radicand, which is the 4 minus x squared, is equal to, so I need to distribute 2x plus 4 times 2x plus 4. So we get 4 minus x squared equals, so you get 4x squared, boiling this out, 2x times 4, that's a plus 8x. 4 times 2x, that's a plus 8x. And 4 times 4, that's a plus 16. 4 minus x squared equals 4x squared plus 16x plus 16. So quadratic, set it equal to 0. Let's add x squared to both sides and subtract 4. If I add x squared to both sides, we get 5x squared. Still have a 16x. Subtract 4 from 16, I'd have plus 12. So I don't like that, but it's doable. So try to factor it or just jump in and use the quadratic. Are there two numbers? Yeah. This is factorable. I can see that because A times C, 5 times 12 is 60. And I can easily see there's two numbers that multiply to 60 and add to 16. Let's rewrite the middle term. That's 10 and 6. So I'm going to rewrite 16x as plus 10x plus 6x plus 12. Factor by grouping. We can pull 5x out, which gives us x plus 2. Plus we can pull 6 out here, so x plus 2. What's inside the parentheses is the same, x plus 2. Pull that out, you're left with 5x plus 6. So we're looking at when is x plus 2 equal to 0? Which is negative 2. Whoops. And when is 5x plus 6 equal to 0? This is negative 6/5. Okay. So x equals negative 2. If you go back to our graph, so here's negative 1, and here's negative 2. And we were already looked at and said we thought that it was going to cross there. At negative 6/5, so that's negative 1.2, about here. It's crossing again. We know the y value of this point. This was at negative 2, 0. And if we didn't know that, we could go back in and plug in negative 2 into one of these equations. Either one would give us back 0 for y. We need to find the y value, though, when x is negative 6/5. Well, I'd go back and I would determine which equation looks the easiest. To me, that second equation looks easier. Y equals 2x plus 4. So y is equal to 2. Let's go back and plug in what x is, and then plus 4. X is negative 6/5. I noticed that we're going to have to get a common denominator, so we might as well do so now. And the common denominator is 5. So we get y is equal to 2 times negative 6, negative 12/5, plus 4 times 5, which is 20/5. So y is equal to negative 12 plus 20 is 8/5. So our other point is negative 6/5, which was our x value, and our y value is 8/5, which is 1.6. If you look at our graph, and 1.6 falls in our domain of the semicircle, so my guess is that we're right. But we can always go back in and plug in both of these points into both equations and show that they both work. But those would be our solutions to that system. I'm going to do one more. So if I had 4x squared plus 3y squared equals 4, and I had 2x squared minus 6y squared equals negative 3. I know, looking at the first equation, 4x squared plus 3y squared equals 4. I can tell right away that this is an ellipse. I have both an x squared, y squared term, but they don't have the same exact number and they're the same sign. I can even go further and I can tell that this doesn't have an x term or a y term other than the x squared, y squared. So this is actually centered at 0, 0. 2x squared minus 6y squared equals negative 3. because I have an x squared, y squared term, not the same number, not the same sign, I can tell that this is a hyperbola. And I can also tell right away that the center is 0, 0. They're almost in standard form. They're not set equal to 1. So they have to be set equal to 1, and the coefficient in front of the x squared, y squared has to be 1 in the numerator. So I could divide all terms of this first equation by 4. If we divide everything through by 4, we'll get it in that form. But instead of me graphing this for now, let's talk about how we would solve this one. This one I would not use substitution method. I mean, it would become really ugly. I'd have to solve for either x or y in one of these equations, take the square root of both sides. So here's a case where using the addition method is good. So our goal is to add both of these equations so that one of the variables goes away. It doesn't matter if you choose x or y. I noticed that the coefficient in front of my y squared terms are opposite signs, so maybe just choosing that to get rid of y. So I need one to be a positive, in this case 6y squared, and one to be a negative 6y squared. So if we multiply the first equation or row, getting in the terminology that we're going to be using later. So let's look at 2 times row 1. So I'm just going to multiply every single term of this equation by 2. So that gives me 8x squared plus 6y squared equals 8. And then I'm going to add it to my second equation, but I'm going to call it plus row 2. Row 2, I'm just going to put below 2x squared minus 6y squared equals negative 3. Putting these notes to yourself is helpful because it's easy to make an error, and going back and identifying what you did is really helpful for you to check your work, but also for me when I'm grading it. If I'm spending like 10 minutes trying to figure out what's going on, then I start getting frustrated when I'm grading it, and more likely not to give you as many points for partial credit. Okay, anyways, so 8x squared plus 2x squared, that's 10x squared. Negative 6y squared, or sorry, 6y squared minus 6y squared cancels, that's why we did that. And 8 minus 3, that gives us 5. So we get 10x squared equals 5. I can use my square root method. Let's first divide by 10. So I get x squared equals 5/10. X squared equals a half. If I take the square root of both sides, I get plus or minus the square root of 1/2. We don't like radicals in the denominator. We can rationalize the denominator, because this is really square root of 1 over the square root of 2. By multiplying by a fancy one, square root of 2 over square root of 2. So x is equal to plus or minus root 2 over 2. So we have 2 values, but that's just the x value of the point. So we need to find y. Doesn't matter which equation you choose. I doubt either one is easier than the other. So plugging it into the first one. So if we plug that in, we're actually going to get the same value either way, because we plug this in, we're squaring it. So we only have to do it once. So we have 4 all times x, so root 2 over 2, quantity squared plus 3y squared equals 4. So we get 4, squaring a square root of 2 is just 2. Squaring 2 in the denominator is 4, plus 3y squared equals 4. I notice my 4's cancel. I'm going to have to get y by itself, so let's subtract 2 on both sides. We get 3y squared equals 2. Divide by 3, we get y squared equals 2/3. Take the square root of both sides, plus or minus. rationalize your denominator. So we get plus or minus root 6 all over 3. Okay, so that means that I have a point at root 2 all over 2 for x and positive root 6 all over 3. I possibly have one at root 2 over 2 and a negative root 6 all over 3. Then for this piece, I have x is negative root 2 all over 2, positive root 6 over 3, and a negative root 2 over 2, and a negative root 6 over 3. I will have to go back and check solutions. But basically you have an ellipse and you have a hyperbola. So it's probably looking like this, and these are your points of intersection. But I don't have enough time to go do that because class is pretty much over. So let's stop there. But I thought that that section was good because it kind of is a good review of going over graphs, and we were just looking at a lot of those different types of graphs.